That should be fine because they're not going to prevent anything.
Right, I think it's
Okay, you're on.
Okay. Sergei Chernyshenko from Imperial
Yeah.
College.
Thank you. Thank you. Okay, well, time is running short. Let me start immediately. And I was fortunate to have quite a few talks here that are very relevant, that will help me actually in what I'm talking about. Now, the idea of this talk came from the name of the workshop, Wall-Bounded Turbulence Beyond Current Boundaries. And as Ivan mentioned, I was lately working on this quasi-steady theory. And the question is, okay, what's beyond? And that will be the topic of this. Yunjiu is a PhD student who contributed to this talk. So this is what I will be talking about. I will give a very brief indication what this theory is. Many of you know, but at least for the rest, something there. And then I will go around the domain of the validity of this theory, trying to see where it actually does not work, where things can go wrong. And after that, we will talk about the future. The general setup is what is common for all of us. We have a wall, we have a turbulent flow, we have inner layer, logarithmic layer, outer layer. It can be a channel, it can be a pipe, it can be a boundary layer. That is the setup. Another most important element of what I'm talking about is a very old idea of wall units, if you wish. So we think in the following way. Okay, we have this flow, and what we can do, we can calculate the mean value of the skin friction, calculate the corresponding velocity, and introduce non-dimensional units based on those and laminar viscosity. If we do this, we have these wall units usually denoted plus, and we use them. What we know about those is that in general, of course, the velocity is expressed in these wall units depends not only on time and coordinates, but also it depends on the Reynolds number, or the geometry of the flow, and everything. Then there comes the idea of universality, the classical one. So if now the Reynolds number becomes greater and greater and greater, goes to infinity, and if we are looking at what happens near the wall, somewhere in those buffer layer, viscous layer, maybe even logarithmic layer, then in that area, the Reynolds number disappears from the set of arguments, as well as other outer parameters, whether it's pipe or channel or boundary layer. In wall units, we expect that statistics of the velocity are the same. A disclaimer. One should understand that when we say this, what we mean is that you specify the statistics and then the Reynolds number to infinity. Because however large the Reynolds number is, if I will be choosing different statistics, eventually I will always find one which will not satisfy that. It is statistic fixed, Reynolds number to infinity. But everyone knows this in this audience, I think. Then the second important element is what Ivan was just talking about, large-scale influence. Because even though those large-scale motions are outside, it turns out that they do affect what happens near the wall, whatever the Reynolds number is. Moreover, empirically, that can be represented in this form. This is a famous formula which expresses the velocity. In this case, it's fluctuation velocity via the large-scale signal obtained by measuring somewhere else, getting the large-scale signal via some filter, large-scale filter. And then here is the formula where, importantly, alpha and beta are empirical functions that are not dependent on large scales. And what is observed simply empirically, that this function appears to be universal. The implication is very strong because you see this one, the large scale function. It is large scale, it is out there. So that is not universal. It changes from pipe flow to plane flow to boundary layer. It changes from one Reynolds number to another Reynolds number, however large the Reynolds number is. And that means that while the statistics of this function might be observed to be universal, the statistics of the velocity, therefore, are not. And that means that we do not have this. Moreover, as MK was showing now, that his results from, well, when the Reynolds number increases, those large scales are getting stronger and stronger. Yes, logarithmically, and we don't know what will happen at infinity, and people argue about this, but that they are getting stronger is just a plain fact. That's it. So what do we do about this? Having something which is universal independent was proved to be highly useful and very, very convenient. But now we don't have this. What instead? Instead, this is the quasi-steady, quasi-homogeneous universality idea. First of all, one should understand that in this world, when large scales do something to small scales, we need to somehow introduce those large scales. So conceptually, we can simply say that if there is some quantity, it can be represented as a sum of large scale component and the rest, which is then small scale component. Once you have this, you can imagine the behavior of this large scale component. That will be time dependent. And it also will be dependent on the coordinates in all parallel directions at least. So this is the video which shows this. This thick line is the wall friction large scale component. Conceptually, on top of it is the large scale component of velocity. And what actually happens, it changes with time, it changes the direction, it changes the magnitude, as the videos show. Now, suppose that we would have this situation. There are two flows with different wall friction, with different direction, different magnitude, and we are in the world of the previous universality hypothesis. Then we say, oh, come on, that the friction velocity is different just requires us to introduce new coordinate system. The different value of this, okay, we should average everything with tau L. And after that, well, we have this universality. So the idea of this quasi-steady theory is that this is exactly what we should do when tau L changes slowly, because it's large scale, and it changes in the wall parallel direction, but not that fast as compared to small scale turbulence. So we neglect this and replace in the usual theory, the universality theory, the mean tau with the mean tau L, or the tau L large. That's the idea. Basically, the near wall turbulence adjusts itself quasi-steadily and quasi-homogeneously to the large scale component of the skin friction. Once you have this, you assume those tilde variables. So that's just like plus units, but with tau L. And you can do derivations. Now, the next thing is, okay, but is it valid? Does it work? I will not talk much about this. I will give only one example because this one was the very first one, and it is in a sense the most impressive one. In this formula, we have empirically found function alpha of y plus. And it was actually found like this expression. It is just the correlation of large scales in two senses normalized with the outer sense. If you take this quasi-steady theory and do some mathematics, which we will skip completely today, you can demonstrate that this should be equal to that, where U capital is the mean flow. I will not explain how. You just do mathematics on the basis of that stuff. And here is the comparison. Dots are DNS, and the theoretical prediction is a curve. So at least in this case, the theory is confirmed. Actually, there are many other confirmations which are symbolically shown here. But today, I would like to concentrate on the situations when it does not work, because that allows me to try to understand what's the boundaries. Every theory has a domain of validity. Every theory outside of that domain will not work. And in order to use it, one needs to know where the boundaries. This is what I am after right now. In order to understand how it is going to work, there are a few key points. First, I will not do any math, but I should say that one big question is, okay, what is exactly large scale? What's that filter is? How do we find it? And it turns out that in order to do theoretical derivations, you don't need to know. It is sufficient to postulate a number of properties of the large scale filter. And if the filter has these properties, then it's axiom, and you do rigorous math from this on. The only question will be, do we have such a filter in real turbulence? And that can be only satisfied approximately. But the math is rigorous. The second point to pay attention to, and again, just was mentioned, that actually, when we do something reasonable with those large scale estimates, the amplitude of the fluctuation of large scales turns out to be pretty small. And it is not growing that fast, actually, with the Reynolds number. So in many, many situations, we can send these two parameters to zero and do Taylor expansions. And that is a method which is often used. But of course, truncating adds an error into this. What is written down there is just a picture. You can have a lot. We will not look at the equations themselves, but you can do those derivations. Another point is that this filter question, filter selection, is something which does not affect the real world. There is a turbulent flow over there, and I'm sitting here and deciding what my threshold is going to be in the filter. It does not change what happens there. This is important. This is very important as dimensional analysis as well. You can use in meters or feet. It does not matter. And basically, if you do this, what is a possibility for us, an opportunity to make comparisons between two different flows, which have presumably the same small scales here, but different large scales. Then this variation is the same regardless of where we put the filter threshold. That immediately translates to the following. Here is one of the formulas obtained using this large scale Taylor expansions. And if you look at this formula, the amplitude of the fluctuations of large scales depends on how you define large scales. So you change the filter, this changes. This also has to change because that is the real world. It does not change. So this depends on the filter, and this depends on the filter. But if I take two different flows and subtract this formula from one to another, this goes away, and that becomes just a value. Even if I don't know this value, because this is a function of wall distance, I can do comparisons. That doesn't require anything. Another point. Well, if you now go back to those formulas and look at these differences, and there are many terms here, but well, this is the mean velocity behavior. It's squared. And if you take the numerical values, say at y plus 40 of this, it is 285. And the rest, which is there, is something like 6. Here again, there is a huge term, 2000 to 200, as compared to, we can just drop those small ones. If we do, we have even easier thing to compare, these formulas, which is very good. And so this is the point where I start checking, Okay, so does it work? Let's now try to compare it with the real data. Here is the real data. This is delta U RMS, this is delta W RMS. And if we divide this by that, even though I don't know the change between two flows, yeah, even though I don't know this, I know that it is independent of wall distance. So it should be horizontal line. Solid line is MK stuff between RE tau 200 and 2000 and 5200. And here is the DNS. And this is by the results for pressure gradient boundary layer, RE tau 3000 and 10,500. And this is these points. And what you see here, that yes, this is more or less constant away from the wall. But here, it's clearly not. The reason is quite simple. It is because we said that this was very large, but at the wall, it becomes zero. So yes, we see the discrepancy, but it does not do anything about hurting the quasi-steady assumption. This is another case. Here it is a channel flow, but we are working with Reynolds stress there. Just today in the morning, MK said that, well, look, there was no correlation when we look at V between large scale and small scale. You write the formulas of the theory and shows that there is no correlation. And this is what is happening for the Reynolds stress here. This curve is the prediction of quasi-steady theory. And this solid curve going down there is the DNS. This is the difference between these Reynolds stresses for two values of the Reynolds number. And you can see that clearly quasi-steady theory is well off. Why? Well, we do know what happens with the total stress in a channel flow as a function of the Reynolds number. Due to the pressure gradient, the total is just a straight line. But, well, okay, as soon as you are slightly away, yeah, you have this, the Reynolds stress becomes large. And so what actually happens in this situation is that this effect, Reynolds number effect, is much stronger than quasi-steady stuff. You increase the Reynolds number, this goes down, that remains. Again, we kind of see the discrepancy, but this is because the Reynolds number is large enough. Here is another example. In this case, we simply look at the skewness, just Ivan was talking about. This is the quantity of interest. Okay, kind of skewness. And well, if you take quasi-steady theory and take only the main term of the Taylor expansion, it is this black curve. You add more terms of the Taylor expansion, and we go towards the DNS result. So if you use Taylor expansion, again, truncation creates problems. This is another thing. At first, the theory was done one-dimensionally, only for one velocity component. But there is a deviation in the direction. It turns out that, well, if you look at the behavior of various quantities as a function of the Reynolds number, URMS changes a lot, and WRMS changes a lot with the Reynolds number. But if we neglect the variation of the direction, we cannot predict this using the quasi-steady theory. If you take into account, we have it. So neglecting of fluctuation as soon as the span y of the direction of friction, as soon as the span-wise velocity is essential, well, that's not the way. You have to take into account this. And finally, this probably is the most interesting element of what we are having here. Large scales. Well, one needs to this is a quantity which obtained in the following way. We take large-scale distribution of skin friction, and then we use the theory to reproduce the behavior of large scales up for higher values of wall distance. And we can also get the large-scale structure directly from DNS. We take the difference and normalize. So here you see these two upper curves for this quantity as a function of the Reynolds number, and it's normalized. So in order for this to be small, it should be smallest compared to 1. It's nowhere near being small at R-tau 1000. When you increase the Reynolds number, it becomes smaller. But we clearly see that before we get anywhere, we need to go to much higher Reynolds numbers. Unless we change the filter. If we increase the cutoff filter, the span-wise scale, yeah, we have improvement here. So from this to this and from that to that. But it is not happening near the wall. Near the wall, we do need to increase the Reynolds number. So that's basically the outline of possible situations where we can go beyond quasi-steady theory. I am short on time, so I have to say what is beyond. There is one thing which is absolutely obvious, and MK, right for you. You showed us a lot using wall units. But these effects, quasi-steady effects, thus described, are very strong even when they don't dominate. And so when you look at the quantities in wall units as on the left, well, this behavior is due to basically large scale, small scale fluctuation as described by quasi-steady theory. You move to tilde units, you have a much more compact behavior. Still, there is a lot left out there. So you just use tilde units, then you will have these quasi-steady effects eliminated, and then you study the rest. That's what is common sense to do. And this is the only work I know so far that actually did this. That's again for many people here sitting. Well, what I would like to do next, we have data for channel flow. We can get from this those universal functions, universal behavior. Then, if there is another flow from which we only need the large-scale friction at the wall, I can now substitute this large-scale friction on the wall into the quasi-steady theory and thus predict everything what happens in this case. Yeah. Anyone offers me a database, please? Okay, I will skip something, one point, because yeah, time is short. And this is the final thing. Maybe what needs to be done is a composite expansion as in asymptotical methods. So we should take quasi-steady prediction and subtract from it quasi-steady predictions for large scales, which we demonstrated at moderate Reynolds numbers are not quasi-steady. And then measure quasi-steady large scale actual and add. Maybe it will work. Here is the conclusions which I actually formulated on the go, so I would stop here. Thank you.
This is not a question, but if you want a boundary layer at R-tau 2000,
Yes.
I mean, it's in my, it has been in my webpage for 10 years now.
Okay, what's the size of the box?
Well, the boundary layer is long, of course. I mean, the boundary layer is...
But I still need to have my large scale filters to fit into this. That's roughly LZ.
It's long. I mean, it's clearly longer than that, of course.
It's okay.
Sure.
We will talk.
No,
we will talk.
It's a very big file.
MK,
very big file.
Philip,
I tell you.
Atame, people. Well, let's talk after that.
Sergei is now very happy, so it's a good time to ask. I was wondering how useful this framework do you think would be for what Ivan is doing because he's doing large scale control, but that is modifying the small scales.
The large scale element of that experiment is totally new to me. And my head already is full of possibilities, but I can't say anything. Thank you.
Thank you. I've never seen these tilde units. What are these tilde units? How well known are they? And do you still have a log layer with tilde units?
Yeah,
You do.
yes, of course.
So how-
Basically, it is exactly the wall units, but tau
it's just a
is
different
tau
tau.
L.
It's just a different tau. How do you find the tau? Is that time dependent, or how do you find the tau?
Because I take the large scale filter and apply to the distribution. Tau is a function of time, x and z. You can imagine, for example, Fourier cutoff.
Oh, I understand. Thank you. Yeah, great.
Well, I think that's the close for this part of the session. So let's thank Sergei again.
Thank you.
And all four speakers from this session. There's two more in this part after the break, but I see somebody with a camera. Is that? Do you want to tell us what?